sharing. Okay, and this is the, here it is. All right. Okay, so good morning, everybody. Again, I have to just take a look in the participants. Okay, the one answer for the Julia, I didn't answer for your email because I thought that the best way it will be give you some information about the tests and something like that by online, yeah, for everybody. That's why I don't send you the response for your email. All right, but maybe we'll start the next part of the material, and at the end I will tell you something about. I will tell you more something about the tests. How I look how I think that should looks like. For example, what will be the material range for you, and we will discuss about it. All right. It's okay. All right. So thank you very much for the people which who sent me the homework. There's not a lot of people who done it. However, I will come back with this to the end of this meeting. All right. So last time I show you how we can use the Laplace transform for calculations of the electronic circuits, and how we can find the mathematical expressions for any type of signals in the electronic circuits, yeah, using the Laplace transform method. As you saw, it is excellent way for electronics, in fact, yeah. Great, but today I wanted to show you and tell you something about two-port circuits and about frequency characteristics. Okay, why? Because it is so important. Because anytime in electronics you will hear about the frequency characteristic, and I just want to show you how we can make the calculation of it, how we can find the mathematical expressions for frequency characteristics. All right, great. So let's starting. Okay, do you see the white sheet? Yeah, okay, so everything is correct. Yeah, okay, great. The first thing, if I will ask you what is the frequency characteristic, so what you will tell me? What is the frequency characteristic?
Is the graph of frequency?
Yeah. Something more about it?
How some device reacts to input frequency?
Maybe yes, in the frequency domain. All right. Okay, so
it depends on the time.
so Could you tell me again?
I think the frequency depends on the time.
On the time, yeah, you can say on the time because the frequency is reciprocal of the time. Yeah. All right. So, do you know what is the amplitude characteristic? Or do you know? Yeah. But in what domain? In time domain?
Frequency.
No. No.
In frequency.
Domain. Domain. It is the x axis. Okay. No. Do you heard something about the phase characteristic? Do you hear something about the phase characteristic? Something like that. All right. Okay. So I just want to check what is the knowledge of you. What is your knowledge about it? And first of all, if you talk about the frequency characteristics, in fact, we are thinking about two characteristics anytime. The frequency characteristics, in fact, are divided by two characteristics: amplitude and phase characteristics. So you will see why I asked you about this two characteristics, amplitude and phase. All right. What is the amplitude characteristics? Amplitude characteristic, it is the characteristic which depends on frequency, and you can see what will be the amplitude of voltages, currents, for example, in frequency domain, depending on the frequency of the signal. So, for example, we've got the frequency here, and here we've got the amplitude, for example, in the volts. Yeah, and the characteristic looks like that. For example, sorry for the why I'm just turned off the autofocus. It will be better. Okay. Okay. Do you see the white sheet here?
Yes.
Yeah. Okay. So as you see, you can see here what will be the, for example, the output voltages according to the frequency. Yeah. What is it? It looks like the audio amplifier characteristic. Yeah. For example, here we've got the down and up frequency corners. Yeah. And this is our bandwidth of our amplifier, for example, amplitude audio amplifier. Yeah. And this is, for example, 20 hertz to, for example, 60 kilohertz. Okay. And what about the phase? The phase characteristic depends on the frequency, of course, but here we've got the degrees here. This is the phi here, the phase. And for example, looks like that. What does it mean? Okay, if you let's starting with the phase characteristic. Please imagine that we've got the black box here. We've got the input and the output. Right? So if we plug in the input signal, which will be, for example, the sine waveform in time domain, as you see, for the time equals 0, we are starting with the 0 volts here, and according to the sine waveform, we will have the magnitude of the signal or the amplitude, yeah, for example. And what will be the phase characteristic? For example, if we, at the same time, if we will observing the output signal, you will see that for some frequency of the input signal, we will get the sine waveform equal, looks like that. For example, the signal is amplified, yeah, but you can see that for the same instantaneous of time equal 0, my original input signal is starting on the 0 volts, but this signal is starting with the -1. It is not starting at 0. The 0 is here. So as you see, we can observe some time delay between the output signal and the input signal. This time delay is defined here, delta t. So in the other word, we can say that the beginning of the sine waveform on the input appears on the output after some time equal delta t. Right. But we know that if we've got the sine waveform, we can redefine the values of the x-axis to the different way for the different one. For example, if we will have the time, yeah, so we've got the seconds. However, we know that the sine waveform can be described as in degrees domain. We know that here we've got the 0, here we've got the pi over 2, here we've got the pi, and here we've got the 2 pi. Yeah, that's right. You agree with me or not?
Yes.
Yes, I agree.
Oh, yeah, thank you very much, Jakub. Okay, so in the other word, we can say also that the sine waveform have some phase, instantaneous value of the phase. Here we've got the pi over 2. Pi over 2, it is in degrees, it is 90 degrees. Here we've got the 180. Here we've got the 360 degrees here. Yeah. So look, coming back to the input and output signal, we can represent the delta t, so this time delay, using the angle. Yeah, it is possible. It is possible. How? Very simple. Look, because this is the frequency f, also on the output we will have the frequency f. So from here to here we've got the period of t. This is the same period like here. That's right, because this is the same frequencies. So we can write that the period t, it is the same like what angle, what phase changed from here to here. That's right. This is the period t, and in angle it is 0 to 360 degrees or 2 pi. So we can say that the period, it is the same like the phase equal to pi. So if you will be able to measure the time delay of the output signal according to the input one, and this is delta t, so it is the x in the degrees domain. So the x can be calculated as the delta t times 2 pi over t. But we know that the period, it is the reciprocal of the frequency. Yeah, t, it is equal 1 over f. So we can write it also in that form. The x, it is the delta t times 2 pi times frequency. Okay, it is the same. And as a result, what we've got, look, this is delta t, it is in the seconds. The frequency, it is the 1 over seconds. Seconds and second is reduced. So we'll have only 2 pi. We have the representation as the radians in the grades, in the degrees. So here it is the radians. Also, we can build our expression for the x in the typical degree domain. Delta t times 360 degrees over t. And then the x, it is in degrees. What is the x? The x, it is the phase shift. This is the phase shift between output and input signal. And now, as you see, we can find the one value of the phase shift for the frequency f. But what happened when the frequency is going up or changed? What will happen here? It will look like that for the changes of frequency, we'll observe the changes of the time delay between the same phase of the output signal according to the input one. So if we are, for example, increasing the frequency, the delta t will be increasing. Yeah. So in that way, we can build the phase characteristic of our circuit, yeah, according to the frequency. And let's coming back here. If you have the 0 degrees here, we can see that if we increase the frequency, the phase are changed in that way. For example, here we've got minus 90 degrees, for example. Yeah. That situation means that the input signal was like that, and the output 90 degrees, shifting by 90 degrees is here, so it will look like that. Yeah, this point is shifted, in fact, on the output by 90 degrees. All right, so that's the phase characteristic. The phase characteristics tell you what is, in fact, the time delay of the output signal according to the frequency. Right. The amplitude characteristic, it is rather simple. The amplitude, it is the question is, if we have the amplitude of the sine waveform, which is equal 1 volts, yeah, and this is for the frequency f. On the output, we will have the same frequency signal, it can be shifted. It can be shifted, yeah. So some phase difference will be observed between them. Sometimes, of course, but we can see that here the amplitude of the output signal, it is not the 1 volts, but this is the, for example, 0.75 volts. Yeah. So what is the amplitude here? We can express the amplitude characteristic if you are just taking the output signal and put it here, the values. However, the better way, it is calculating here as the amplitude the proportional between the output and input signal. For example, as the V out over V in. Yeah. And then that expressions will be on the y-axis, and that also will be the amplitude characteristic. All right. So if the frequency is changed, we're observing the changing in amplitude on the output. Yes, yeah. Do you have some question? Okay. So please tell me, do you understand what is the amplitude and phase characteristics? Hello? Okay, never mind. So one thing, if you will get some example, please define or please find the expression for frequency characteristic of some electronic circuits. It means that you have to find the amplitude and the phase characteristic. Anytime, you have to remember, frequency characteristics consist two, amplitude and phase characteristic. Okay. Or maybe on some example, you have to please find the expression for the phase characteristic. In such way, you have to only define one characteristic, the phase characteristic. Okay, great. That was the first thing. Now, I wanted to show you how we can find the amplitude and the phase characteristic for some two-port circuit. Okay, let's starting with some very rather simple circuit. It is something like that. Okay, and this is the input, and this is the output. We've got a two-port circuit. We've got the input and the output. Okay, 4 terminals. Okay, this is the V in, and here we will have the V out. Great. The first thing we have to define something like the transmittance of the circuit, of the two-port circuit. What is the transmittance of the circuit? The transmittance T show you how looks like the ratio between the output and the input signal. In the other way, the transmittance, it is the V out over V in. Okay, so as you see at this moment, this is the transmittance. This is the complex number. This is the complex number. Why? Because we can observing the changing in changing of the output signal in changing in amplitude and the phase. Yeah, so that's why the transmittance, it is the complex number. This is the complex number. Okay, however, in general, this is the transmittance. It is V out over V in. If you're coming back to the amplitude characteristic, I told you that the amplitude characteristic can be defined like the V out to V in. Okay, so as you see, it is possible to find it. But if the transmittance, this is the complex number, so the t vector can be, for example, here, and the length of this vector, it will be the modulo of t. That's right, the length of the vector, the value of the vector. And here we've got the phi, the angle. And if you will be able to calculating the transmittances of the circuit, in fact, we can find the amplitude characteristics, which is hide in modulo of t, because this is the value or how the V out changing due to the V in. And the phase characteristics is hide in form of phi angle. Yeah? This is the phi characteristic. The omega is 2 pi f, so I'm just writing in that form. So that will be the amplitude characteristic, and that is the phase characteristic. Okay. All right. So if we want to find, one question. Do you understand it at this moment? Do you understand it? What I talk about it? What I told you about the transmittances? about the transmittance.
Yes.
Okay, great. Oh man. So the question is how we can find the amplitude characteristic. We have to calculating the modulo of t, how many it is. If we wanted to find the phase characteristic, we have to calculating how the phi angle are changed due to omega. And here we have how the modulo of t are changed due to omega, due to the frequency, in fact. Okay. So the first question is how to define or how to calculating the transmittance. Okay. Before it, because we are operating on the complex number, it means that we are operating in the AC domain. Yeah. We've got the signals which has some frequencies. So we have to operating on the impedances. Okay, so we know that the impedance of the pure resistor, it is just the R. My question is, what is the impedance of the pure capacitor? How many it is, please tell me. In the frequency domain. Any ideas? Oh, come on, guys.
1 divided by omega times capacitance.
Yeah, That's right. 1 over omega c. That's right. This is the impedance of the pure capacitor. For the coil, it is equal omega L. Yeah. That's right. That's right. Great. So let's find the T. Okay. Before it, please tell me, do you see something special in this circuit? I mean, we can use some method which was commonly used in electronics to calculating how many it is the V out. What is the value of V out here?
A voltage divider.
Yeah, that's right. That's right. We've got the voltage divider here. So please tell me, in general, what is the V out value if you will use the voltage divider expression for this example? It is the what?
V in
Yes.
times C over the sum of impedances.
No. No C.
Impedance of
ZC?
Yeah, that's right. The impedance of the capacitor, yeah? Not the capacitive C, the capacitance C, but it.
Yeah, my mind just made some kind of shortcut.
Okay, don't worry. But we have to be much more precise. The impedance of the pure capacitor, it is what? In general, it is the resistances, yeah, plus minus J X. That's right. The X, it is the reactances, yeah. And the pure capacitor, because there is no any resistances, yeah, we've got only the XC, it reactances. That's right. So in fact, the 1 over omega C, this is the reactances of the capacitor. Yeah. Omega L, this is the reactances of the pure coil. But the ideal coil hasn't any resistances. So the XZL, the impedance of the pure coil, it is equal 0, yeah, plus some J omega L. That's right. So that's why the impedance is 1 over omega C, and for the coil it is the omega L. All right. So it will be the impedances of the capacitor over the sum of the impedances in our sorry in our voltage divider. So this is the the impedance of the pure resistor plus impedance of the pure capacitor. Right. And this is equal V in times ZC. In fact, this is for the capacitor, this is the XC over the resistances plus XC. Okay.
I'm sorry, we are not placing minus because it wouldn't make sense in voltage.
No, we don't use the minus here. It is okay. It is in general, yeah. And look, if I will divide both sides of the equation by V in, as you see, I will get the V out over V in will be equal, V in will be reduced in the right side of the equation. I will get the XC over R plus XC. Okay. So as you see, what is the V out over V in? This is the transmittance. Yeah. All right. So our transmittance is given by that formula. XC over R plus XC. All right. So now let's substitute by the values of the XC and the resistances. It representation like the 1 over omega C in this case, and the pure R. Okay, I told you that the minus is not important here. However, the J, it is important. We have to indicate which components has it is the imaginary part of the transmittance, and which one it is the real number of the complex number of the transmittances. So so in fact, this minus, I told you that the minus here, it is not important. However, why? Because it depends how we can represent the J. Please tell me how many it is the 1 over J. How many is 1 over J?
Minus J.
This is the same like the minus J, yeah, because we have to multiply it by conjugate number minus J and minus J. In fact, gave us the minus J. That's right. This is the same as you said. So if you are coming back here for the pure capacitor, we've got the R minus JXC. That's right. Minus J can be, because the R is 0, minus J can be replaced by 1 over J. It is positive. So here, this is just the reactances. Yeah. However, here we have to adding the J, because we have to indicate which components it is the imaginary part of the transmittance. So if you want to be much more precise, ZC, it is in fact equal minus J XC. And the ZL, it is the J XL. Okay, so XC can be represented in that form, minus J 1 over omega C. ZL, it is J omega L. Okay, if you will substitute by minus J 1 over J, we'll see that the ZC, it is the 1 over J omega C. And the ZL, it is equal just J omega L. There is no, we don't have to change nothing here. So that's why I told you that the plus and minus here doesn't matter, because we don't have to take it into account, because anytime we'll have the positive value here as the XC if you use the J indicator, but you have to remember the J is going down here. It is 1 over J. Okay. Okay, so the xc, it is equal 1 over j omega c. The r, it is equal r, just r, yeah, the impedance of the pure resistor is its resistances, plus 1 over j omega c. Okay, so this is equal. What we can do here, we can find the common denominator here. It is j omega c. So the 1 over j omega c times this components, I move it here, 1 over the common denominator is j omega c. So we will have the 1, it is here, plus r multiplied by denominator. So it is j omega r c. Okay, you've got it? Great. So as you see, j omega c can be reduced with this. And we've got 1 over 1 plus j omega rc. However, this is the representation of the transmittance. But as you see, we've got in denominator the complex number. So what we have to do, we have to multiply the denominator and the denominator by the conjugate number, according to this one. So it will be the 1 minus j omega rc, 1 minus j omega rc. Okay, and this is equal. In the denominator, we will have multiplied by 1 everything. So this is the 1 minus j omega rc over, and here, as you see, we've got the situation where we have the a plus b times a minus b. Yeah. So this is equal a squared minus b squared. This is the same, yeah? That's right. Okay, we can multiply it step by step, yeah? But we can use this expression for such mathematical properties, using that mathematical properties. So it will be a, it is 1, so it is a squared. So this is the 1 minus b squared. B squared, it is the what? J squared omega squared r squared c squared. But we know that the j squared, it is minus 1. Okay? So the transmittance will be equal 1 over j omega rc over 1 plus omega squared r squared c squared. As you see, the transmittance, in fact, this is the complex number. This is the complex number. Okay, I have to take another one piece of paper. And the transmittance can be calculated or can be expressed in that form. It is the 1 over 1 plus omega squared r squared c squared minus j omega rc over 1 plus omega squared r squared c squared. Yeah. So we can say that the denominator, it is some mathematical expression here, and let's call it like the m, yeah, uppercase letter m. So in the other word, we can say that it's 1 over m minus j omega rc over m. And this is the real part of the transmittance, and this is the imaginary part of the transmittance. Okay. So it looks like that. 1 over m, it is the RE, the real part. This is the minus, so it is going down. And here we've got the imaginary value of this expression. It is here. So our transmittance vector, this looks like that. Yeah, this is the transmittance. Length of this vector, it is the module of transmittance. Yeah, and the module of transmittance, it is our amplitude characteristic. The phase here, this is the phi, it is the phase characteristic, in fact. And if I will change the omega, in fact, we are changing the frequency, this vector will be changed. Its magnitude will be changed, and the phi will be changed. So it will be changing in a different way here. All right. Please tell me, do you understand it? For this moment, it is clear for you? I make it very, very slowly. It is clear?
I think yes.
Mm-hmm. Okay.
So now we have to calculate the module, yes?
Yeah, that's right. So because we wanted to find the amplitude characteristic and the phase characteristic, so if we are coming back here, the amplitude characteristic, in fact, this is the module of t according to omega. Phase characteristic, it is the phi, this is the angle characteristic according to the omega. That's right. So let's calculating the amplitude characteristic. So we have to find the expression for module of t according to omega, yeah, because it depends on omega, as we see. Omega, in fact, the frequency. Okay, and now, because you are great in math, please tell me, what is the module of t?
We can find it from Pythagoras.
Yes, that's right. We can find it using the Pythagoras expression, or we know that this is the vector, yeah? This is the vector, yeah? That's right. And the length of this vector, in fact, this is equal what? Square root of what? According to the Pythagoras equation, yeah? It will be equal how many?
EM.
Sorry?
IM. Is it IM?
The IM, yeah?
M
Plus-
square and R square.
No, okay, I see that we've got some problems. Okay, this length of this vector, according to the Pythagoras expression, we've got the t squared is equal the real part of the number or this vector real squared plus imaginary part of the vector squared. Yeah. So if we wanted to find the module of t, we have to just calculating the square root of RE squared plus imaginary part of the square. That's right?
Yes.
Okay, so in fact, this is the real part of our module of t squared plus imaginary part squared. That's right? That's right. So this is equal square root of. Tell me, how many it is the real part of the transmittance value?
1 over m.
Great. 1 over m squared plus, and what I have to put it here?
JWRC.
Hmm?
No, WRC only.
Yeah, that we cannot put it here the j. Yeah, we cannot put it j here. Why? because the J, it is the indicator that this number on this value, it is the imaginary part of the transmittance. So we cannot put it here, the J. J indicates only that we've got the imaginary part number. Okay, so it is sometimes the student makes some the missing that like that, yeah, they put it here, the J. No, you can't. So the imaginary part of the transmittance, it is equal omega R C over M. Of course, the minus, yeah, because this is the minus before it. However, anytime we have to power it by 2. So in fact, this doesn't matter if we have the minus or plus here, yeah, because any time we'll have the positive result, powering by 2 the expression here. Okay, so this is equal the 1 over m squared plus omega squared r squared c squared over m squared. Great. Okay, you can see that we've got the same denominator, yeah. So it is the 1 plus omega squared r squared c squared over m squared. Okay, so now let's coming back with the substitutions here, and let's substitute by the m, in fact, the real value, which is equal 1 plus omega squared r squared c squared. Okay, what you can see here, do you see that numerator and denominator in fact consist the same expression? I think yes. So this expression can be reduced with the power of 2 here. So what we've got? The square root of 1 over 1 plus omega squared r squared c squared. Do you see it? Your processors are burning or not? Because you don't want to talk with me. What happened there? Are you still there?
Yes, that's all right. I'm just trying to figure out how to calculate phi.
Aha. So we can make it faster, everything? Maybe yes, maybe not.
I mean, there is like three or four people that are actually talking here, so.
Where?
Like responding, so.
Okay. Great. So as you see, this is the module of t, depending on the frequency. This is the mathematical expression for your amplitude characteristic. This is it. It is square root of 1 over 1 plus omega squared r squared c squared. So at the end, I will run the LTSpice and I will see. I will show you how it looks like in real. Okay. Maybe now. maybe now it is good idea. Okay, I'm just run the LT Spice. Okay. Okay. I'm just switch on to the LT Spice here. All right. I'm just put it here the typically. Oh, sorry. Just take the keyboard. This is the resistor. We've got some capacitor. Okay. This is our output signal. Let's put it here with some value on 100 ohms. For example, 100 microfarads. And we have to add the voltage source. Because we wanted to make it the AC analysis. So let's put it here, the DC, the sine waveform here. Amplitude, it doesn't matter. The frequencies doesn't matter. We have to just put it here, just some value. That's all.
Omega is 2 pi frequency.
Sorry?
Omega is 2 pi frequency.
Yeah, 2 pi f. Yeah, that's right. The omega is 2 pi f. Okay. And now I will just run the simulation for AC analysis. 100 points per decade. We are starting with, for example, 1 hertz, and we'll stop on the 1, for example, megahertz. Oh, yeah. Okay. Great. And let's see how it looks like. The amplitude characteristic. Look, the solid line here show you how it looks like the amplitude characteristic, and the dot line here, it is phase characteristic. It is given here. Do you see it? So the scale at the right hand, you have the phase, and on the left hand you have got the scale for amplitude characteristic. This characteristic is represented in the decibels. So, however, you have to take it into account that the x-axis here, it is the frequency, of course, but the axis, it is in logarithmic scale. Okay. If you will change it to the linear one, our amplitude characteristic will be looks like that. Okay. I will change the sorry, where it is, here it is. I will just focus what happened at the beginning here, and again. Okay, so the characteristic is starting from the 0 decibels and going maybe that. Oh, maybe that is going from 0 and starting to decreasing like that. Okay. So as you see, that's why you are using the logarithmic scales in electronics, because as you see, it is very hard to observe on the linear scale what happened with the amplitude. Yeah. So that's the reason why we use the logarithmic scale a lot of. Yeah. And then we are focused using the logarithmic scale. We are focused what happened for the very, very low values here, according to logarithmic scale. One thing, this is not a linear function, yeah, in linear scale. However, as you see in logarithmic, we've got the signal is dropped here, and this is the straight line here. Yeah, you have to be very careful what kind of characteristic you will observe. You will observe. You have to take a look on the scale on your characteristics. Yeah, because at the first look it looks like that our signal are decreasing as the linear function according to frequency. No, it is not true. It is not true, because the frequency axis, it is in logarithmic scale. Yeah, so please be very careful for it. Okay. So
sorry.
Yeah.
So if this is a linear function, obviously in logarithmic scale, we could find coefficient, right?
Yeah, that's right. That's right. Yeah. And what is the coefficient here for this circuit?
My wild guess is that for filters is 3 dB.
No, you are talking about different things. Okay. First of all, what is the decade here on the frequency axis? Decade, it is the changing of frequency by 10. Yeah, decade. Decalogue, decade, deca. It is the, like the prefix is 10. Decalogue, 10 words. Decade, yeah, the changing of the by tens. So from 1 to 10 hertz, we've got the changing by 10 times. From 10 hertz to 100 hertz, we've got the changing by 10. So as you see, from this point to this, we've got the same distance like from this to this. So the decade, it is the distance between this point to this point, this point to this point, and so on, from this point to this point. Yeah, you see it? Do you see it?
Yes.
All right. So the question is, how quickly the characteristic, what is the slope of this characteristic on the logarithmic scale for 1 decade? Look, let's find, because we wanted to get much more faster. For example, we've got the minus 20 dBs is here. Oh, here it is. This point gave us very nice number. Minus 30 dBs is for that value. So the 1 decade, will be where? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is this point. So it is here. So if I get another one, as you see, it is around. Of course, this is the simulation. It is around. What is the differences on the amplitude characteristics when we are changing the frequency by 1 decade?
21 dB.
20, yeah, of course, but this is the simulation. Where it is? 1, 2, 3, 4. 1, 2, 3. Ah, sorry. It is here. Here. Okay, this is the 10. This is the decade. So what is the changing? Is
20.
20 dBs. So you have to remember that this circuit has the slope on the amplitude characteristic equal minus 20 dBs per decade. Okay, and we express it in that form, minus 20 dBs per decade. So that's the f in logarithmic scale. This is the slope of it. Please tell me, do you see somewhere else our circuit, and maybe you will be able to name it? What is it?
Low pass filter.
Yeah, RC filter. Yeah, that's right. This is the RC filter. Yeah, but this is the low pass filter. That's right. Why it is low pass filter? Because as you see on the amplitude characteristic, the output signal according to the input has the 0 decibels. Yeah, and if the frequency are increasing, we're observing that the output signal is decreasing too. Yeah, what does it mean? Look, for the 1 kilohertz, we've got minus 56 dBs. How many it is? How many times this output signal is lower than input one if it amplitudes or it amplitude characteristic for this frequency is equal minus 56 dBs. Yeah. We will calculating it. Okay. How we can find this value? Very simple. You have to know that how we can make the conversion from the decibels to voltages and opposite. In decibels, the number in decibels is equal for the voltage signals, for the electric values, not for the power, but only for the electric values, not the optical power, but for the electric values like the voltage, current, and so on. It is 20 logarithms with 10 base from the V, some value in voltages. Sometimes for the amplitude characteristics, it is the V in or V out, V out over V in. Okay. So how many it is the 0 decibels? How many it is? 0 decibels is equal 20 logs with base 10 from X. How to calculate the X? We have to multiply the both sides of the equation by 20. Yeah. So the 0 over 20 is 0. And the X can be calculating like the what? The base, it is 10 powered to this value, 0, and this is the x. 10 to 0, it is how many?
1.
1, of course, yeah. So look, the 1, it means this is the V out over V in. What does it mean? V out is the same like V in. Yeah. Okay. So if the V in is 1 volt, V out is 1 volts. So 0 decibels tell you, where it is? Here. No, here. 0 decibels tell you that in this range of frequency here, where we have the very flat characteristic here, the output signal is the same like the input one. So that's why in this range of frequency, in fact, our filter it is not a filter. The signal is passing through by it without the changing in amplitude. But from the 10 hertz, if the frequency is 10 hertz and is starting to increase, as you see, the output signal is decreasing. And going down with frequencies. So that's why this is low pass filter, because the low frequencies is passing through it and the high is blocked. So how many it is? It is minus 50 decibels. Okay. How many? It is the minus 50 decibels. Okay. Minus 50 decibels in our case, it is for the frequency equal 5.2 kilohertz. Okay, so let's turn on the white sheet and let's find how many it is minus 50 decibels. It is in the voltages. So as you see, this is minus 50 over 20 is equal log 10 from x. So the x, it is equal 10 powered to minus 50 over 20. So the zeros can be reduced. This is the 10 powered to minus 5 over 2. Okay. I will just take the calculator. Okay, I got it. And okay, this is the 10 powered to 5 over 2. Ah, oh my, what? How many it is? I will check it again. Minus 5. Aha, I multiplied, sorry. It is 10 powered to minus 5 minus over 2. Okay. Okay, it is 3.16 times 10 to minus 3. So the x, it is equal, if I move it by 3 position, I will get 0.00316. The x is here. As you see, the output signal is lower by this value according to the input signal. If the input signal is equal 1 volts, the output signal will be equal 1 volt times this value. So it will be equal 3.16 millivolts. Yeah. For the frequency, it was I don't know, 5.2 kilohertz, yeah? That frequency is attenuated from 1 volt to 3.6 millivolts. And this corresponds to minus 50 dB. Okay, and because this is a nice opportunity to tell you that sometimes if you're operating with, for example, the RF analyzer, sometimes on the y-axis you can find the dBm value. dBm value, what does it mean? dB, or sometimes is for the voltages, put it here, the V. It means that if we've got the X value, it is V out over V in, and this V in, it is it is like the reference for the output signal. And if you have the dBV, it means that V in, it is 1 volt. This is the minus 50 decibels according to 1 volt reference. If you have the dBm, it means that we've got the V out over, or references to 1 millivolt. Okay, and then the 0 dBm means that the output signal, it is equal 1 millivolts, because then we've got 1 millivolts over 1 millivolts, it is 1. And 0 dBm, it is the same like the 1, of course, 1, but according to 1 millivolts. So in fact, the V out is 1 milli. But it is just, by the way, information for you. However, let's come back here. We know how to make the calculations from the linear scale to decibel scale. Yeah. The one thing, because Jakub mentioned about some specific point, in fact, for the filter. The question is, okay, let's coming back here. The question is, because this is the low pass filter, and we can say that for some frequencies, the filter is working, is passing the signal, and from some frequencies, the signal is blocked. Yeah. However, of course, we haven't the ideal filters. Yeah. The best filter which can be imagined, yeah, for example, the best low pass filter will have the amplitude characteristic looks like that. Yeah. This is, for example, 0 decibels, and this is minus, I don't know, 100 decibels. Yeah. So in fact, we haven't nothing. We haven't almost the any signals here, and this is our FC frequency. Yeah. This is our corner frequency or cutoff frequency for the filter. It means that low pass filter is passing through the frequencies from 0 to FC, and from FC, the signals are blocked. Yeah? But this is the ideal case. We know this is not true. With the real circuits look like that. They have such functions. So the question is, where, for describing the properties of the filters and determine the cutoff frequency, we have to choose some point on this characteristic specific for the cutoff frequency. Yeah. And in electronics, the people are decided in electronics that this point where we've got the cutoff frequency, it will be the -3 decibels position. It means that if we have the maximum amplitude here, so we have to drop it by minus 3 dBs. And for this point, we have to read the frequency, and that will be the cutoff frequency for the filter. Also, if we are talking about the audio amplifiers, for example here, the 3 decibels drop of the signal from the maximum show you the up and down frequency. And between them, we've got the bandwidth. Yeah. All right. But if I talk about the audio amplifiers, sometimes we can buy the very nice amplifier which is named like the hi-fi equipment. Yeah, for hi-fi. Sorry, the hi-fi amplifiers have the bandwidth described like the FD to F up frequency, but not for the signals which drops by minus 3 dBs, but for the dropped by 0.1 dBs. 0.1 dBs, it is very low drop of the amplitude in signals. It means that hi-fi equipment we can assess in all bandwidth has almost very flat frequency characteristic than typical audio amplifier which is not hi-fi. Why? Look, we have to calculating how many it is the drop signal by minus 3 dBs. Let's check it. Minus 3 dBs, it is for the voltages and currents and so on. It is the 10 logs, 10 with some x. Yeah? So very quickly, it is minus 3 over 20. And the x, it is equal 10 powered to minus 3 over 20. Okay. I will just use the calculator. Minus 3 over 20 minus 3, where it is minus 3 over 20. Okay. Okay, what happened with the minus? Minus. Okay, that's correct. Okay, again. 10 powered to 3 minus divided by 20. Okay, so as you see, this is equal 0.7079 and so on. What does it mean? If our signal is dropped by minus 3 dBs, it means if you will have the 1 volt on the input, on the output, the signal is dropped by minus 3 dBs, it means that its magnitudes decrease according to the 1 volts by that value. So it will be 0.707 volts. So as you see, the minus 3 dBs for the electric signals drops. It means that the amplitude is drops around by 30%. Yeah. Okay. So now you will see what the differences between hi-fi audio amplifiers and the cheaper one. Yeah, the typical one. Look, if our down frequency, yeah, okay, for the amplifier, for example, is specified as a 20 hertz, yeah, here and here, yeah, for hi-fi and the typical one. It means for the typical amplifier, it means that for the 20 hertz, our output signal is decreased by -3 dBs. So it means that signal on the frequency 20 hertz is lower than maximum signal by 30%. Yeah. So, for example, that's why if you plug in your loudspeaker to amplifier, and you will have the very, very low frequencies of the signal. This is the buses, in fact. Yeah? You will see that the buses on the loudspeaker is a little bit weak, especially for the very, very low frequency, for example, 20 hertz. Why? Because for this frequency, the signal amplitude of the electrical signal which is going to your loudspeaker is lower by 30% as the maximum. Okay, and now for the hi-fi equipment. Okay, we have to pay much more for it, but for the same bandwidth and for the same frequency, down frequency, which is 20 hertz, we will have, it is specified for drop on the amplitude by -0.1 dBs. Whoa, 0.1 dBs. Let's check it. How many it is -0.1 dBs? It is -0.1 over 20 powered 10. This is the x. Okay, let's check it. Are you still there? Because we
Yes.
Yes.
okay, so there's no any problems with connections, yeah? Sorry for that, but for some times I will ask you that you are there because I have to know that nothing happened with the Zoom. Minus over 20. Look, it is 0.98. It is almost 0.99. It means that for the signal equal 1 volt, for such frequency, when the amplitude is decreasing by 0.1 dBs, we'll have 0.98 volts, almost 1 volt. Do you see it? So this is the drop of the signal is equal 1%. 1%. So that's why for the same bandwidths and the same down frequencies, if you will, for the same loudspeaker, if the same loudspeaker will be connected to the hi-fi equipment, the 20 hertz will be much more stronger. Yeah, it will be much more stronger than for the typical one. Okay, that's the few information which is much more practice, in fact. However, it is nice opportunity to tell you about it.
Can I ask a question?
Yes.
So let's say we have task of creating switching converter with frequency, let's say 100 kilohertz, that will generate 5 volts with ripple 50 millivolts. We can calculate drop in decibels and then choose components of filter to achieve that ripple.
To reduce the ripples.
It calculate what filter we need to have this 50 millivolts at this frequency.
Yeah, we can. Yeah, we can. We can. However, in DC converter, it is work in another way because we have for the DC converters we have to get the DC signal, in fact, on the output. And we have to filtering the switching signal by filter, which is very low pass filter to get the very, very low ripples, and on the output get the almost the fixed DC signal. Yeah. So here we have to use the rather huge capacitances capacitance to decrease this point, the FC, to the very, very low frequencies, few hertz, for example, 10 hertz. That means that the frequency where we observing the switching is much more reduced or not, and it is stopped by our filter, and on the output we'll see only the DC level of the signal.
Yeah, because cutout frequency will give much higher.
Much higher. Yeah, that's right. Yeah, yeah, great. Okay, so we know what is the -3 dBs. What is the slope of our filter characteristic? Where it is? Here it is. Sorry, here it is.
Sorry, excuse me. I would like just to remind you that we're quite like 10 or 11 minutes after our time, so and we still need to discuss the test and the homework.
Okay, today we've got the 4 hours, yeah?
No, 2 hours.
No,
Edukacja says that only 2 hours.
We had 4 hours last week.
Last week? Oh man. Oh, kurczę. I forgot it. I thought that we've got the four hours. Okay, so thank you so much that you remember me about it. All right. Oh man, it's not good. All right. So first thing, because nobody write me the email that somebody has the problem with the cameras, also with the camera which is on your phones. So I suggest that we can write the test from the classes in the next week. Yeah, and we'll make it online. And I just want to tell you how I see it. You have to prepare your cameras or the mic or the cameras from your phones in such a way that I will be able to see you sitting on the desk. I have to see your hands. I have to see, in fact, your body and the mouse. The mouse, if you will writing the test, should be put at the 1 meter from you. Okay. And if I will see you that you are on and you just writing on your piece of paper some exercises, you haven't any mouse, the computer mouse, then if you write it, I will be ask you to use the phone and make the picture of your sheet of papers, and then you will have, I don't know, 5 minutes to send it to my email. It is possible to realize it in that form.
And the camera thing is not really possible, I think.
Why?
Because like not all of us have the thing, like the camera, and then if we do it on the phone, I don't think everyone would be able to put it in a way that you see everything.
How would we mount the camera? Where will we put it?
From your phone, for example, yeah?
Yeah, but then you won't be able to see everything.
Yes, I can put it on my desk.
Yeah,
But,
you have to
you
just
cannot. Okay.
I don't think so that is so problem. Yeah.
I mean, you wouldn't see everything then. That's
I
what I'm
don't-
saying.
You know, I don't. It is not possible to see everything. Yeah. I won't just observe you by the camera. That's all.
Okay.
Sitting on your desk. Yeah. I have to see you and that you written it, that you write the exam your own. Yeah. And I have to see that the mouse, the computer mouse should be put it somewhere else. Yeah, I have to see that you have a possibility to use the mouse and checking something in the computer, and especially that you not make do you not communicate with the others by some other chats, messenger, or something like that, because I know that students are make it in that form. We know that. Believe me, we know that.
And we have the lecture exam next week as well. So
Yeah.
I don't know what my classmates think, but could we?
But from the lecture?
Yeah.
Mr.
Wonj said it like that, and we have the physics exam also next week. So is it possible for you to make it later?
When?
I mean, we are like 36 people here, so I think we should talk together before I say something. But like at least the next like 2 weeks, like not next week, but the other week.
But the other day, yeah, and the other for example, hour, yeah.
What do you mean?
In the different term, yeah.
No, same day, but we have like
the same day.
Yeah, same day, same time, but we have so many exams and we want to prepare.
All right, I understand it because I thought that you are thinking about the completely different day.
No, just same time, but like the other week.
Okay, it is possible. Yeah, of course. Yeah.
Okay, so guys talk and give some propositions maybe and say when is it.
Yeah, that's right. And Julia will write me the email what the hour is better or it is the best for you.
Mm-hmm.
It is correct? It is okay?
To be 100% clear, same day in the next week.
Yeah, at the same day in the next week. So it will be the Tuesday, yeah?
Yeah, everything is the same, but just the week is different because we have too many exams and we won't be able to prepare.
Okay.
Yeah. And until when do you have to have this exam?
But one thing I have to say, what is the range of the material for it? Yeah. This is very important for you. Because the question is, this is another way. The question is, do you want to have the exam or the exam from the or test from the classes from whole material at the once time, or you have to divide it by 2 parts? For example, in the next week, on the hour that you will write me, when you will be able to write me in the next week, we can make it, for example, 1 part of the material, and in the next week we can make, or for the 2 weeks, we can make the second part of the test from the completely different material, for example, from the Laplace transform, or maybe we can compress it, and I will be able to prepare, for example, 4 exercises which will consist DC network, AC network, for example, the power transfer theorem, and the one exercise with the Laplace transform. And then, for example, we'll write only one test, for example, in the next week, yeah, from whole material, almost whole, yeah, without today's and the next ones. And then at the last terms, I will give you also the possibility to make the retake terms also.
So, what if did we do it partly, like you said, part 1, part 2?
Yeah.
But part 1 in 2 weeks and part 2 in 3 weeks.
Yeah. So of course we have to make some retake term also. Yeah.
Yeah, and then the retake would be next week, or the like in 4th week. So 26th of June would be, and then 19th of June would be part 2, and then 12th of June will be the part 1.
Yeah.
So how does it sound to you? Is it like okay for you? Because we know that you have to like give grades and stuff for the school.
Yeah, that's right. The problem is with the grades, yeah, because before we gave you the grades from the lecture, we have to have the grades from the classes and the laboratory, yeah, because the lecture is not ending by the final exam, so we have to have whole grades before session.
But isn't it changed?
What do you mean?
Yeah, the session lasts until September, theoretically, he says. So when does it start?
No, September. What do you mean the session? No.
You mean like
when
the exam session, right?
No. When the session is starting on this semester?
On the 17th, I think.
But it lasts all the way until October. I feel so.
Yeah, they longer that.
Yeah, this is the longer, but when it's starting, because
17th, they say.
17th. So we have to.
No, sorry, the 18th. So
18th.
Yeah.
Okay, so we have the some grades to the end 18th. Yeah.
But is it? I mean, this is the situation in the normal case. Is it still like that? Because the situation is different now. So maybe it is different. Do you know anything about that?
So okay, so I will ask the people from the dean how we can make it, and if this term can be changed, in fact, and we can go to the session and make some and put the grade into the
because
system.
some classes did start really late and they don't have the session exam, but it will be that they have to do some exams during the session, even though it's not a session exam.
I see. Okay, so in fact, it is possible that we are not limited by the time, in fact, at this moment.
Yeah.
But I will check it. So, what do you think about this? My proposed the way how to make this test.
I think
acceptable.
I think people would agree to have it in 2 parts and on consecutive weeks, like let's say in 2 weeks and 3 weeks, let's say.
Okay, so
they need to talk.
We'll write you an email in like an hour with our thoughts.
Yeah, that's right. So please give me the information. How many parts you want? 1 or 2? Yeah, that's one thing. The cameras is needed from your phone or some of the others, and that's all. And please tell me one thing. Adam Wąż told you that in the next week you will have the test from the lecture.
Yes, seems so.
Yes, he said that the test will be on the 11th, and No, on the wait on
Fourth.
the fourth, and the retake will be on the 10th. Sorry.
Uh-huh.
And he plans to do it like multiple answer test.
But he told about the test only from his part, yeah?
No, both of you actually. I mean the lecture.
So okay, wow, okay, that's okay, because I was thinking that that they make the test only from his part. So it will be total test from my and his part.
Yes, exactly.
Okay, excellent.
Wait,
Okay.
can you repeat again? I couldn't hear.
Sorry?
Can you repeat again? I couldn't hear.
I thought that the Adam Wąż tell you that in the next week you will have the exam test from the lecture only with his part, but it is not true. It will be the part. It will consist my and his part. That's right.
Yes, that's right.
All right. Okay. So now it's very clear, and this is correct. Because we talked about each other about the test. So okay, everything is okay, is clear. Okay, great. So what else? So please give me the information on the email what you decided about the test from the classes. Okay.
And you will let us know with the session thing, right? If we have to do it before or right? Hello?
Yeah.
So you would tell us that if we would have to do it before the session or during, like we can do it during the session as I asked.
Okay,
so,
I will give you some information. I suppose that I will send it to Julia.
Yeah, Julia will send you an email. We will talk about it in the group, and you can talk.
But I have to ask in the dean about this session terms.
Mm-hmm.
Okay, and then I will send you the information by Julia.
Okay.
Okay.
Yeah.
All right. So, thank you for today meeting.
Mm-hmm.
May I
One more
ask a
question
question?
about homework.
Yes. About the material range.
Homework.
Yes. Okay. So the people who send me the homework solution and the results, I think that they pass at the maximal point the example with the Laplace transform, which will be on the test. What do you think about it?
Okay.
Yeah, all right.
Sure.
Okay, but only the people who send me the answer.
What is the deadline for that answer?
No,
I can send it right now.
the deadline was for today.
Yeah, so we still have
I
time.
gave you the homework last week, and I told you, and I request you to done it and send me to the next week. Yeah. Only few people are make it. Sorry. So I think these people can make that bonus like that. So you don't have to, in fact,
Przepraszam, chłopaki, jestem.
you will not have to writing the example with the Laplace transform, which will appear on the test, because from this example based on the Laplace transform, you will get the maximum value of the point.
Ooh. What if we didn't learn Laplace before and we had time this week to learn, so it didn't manage?
Sorry.
I'm guessing then that our solutions were correct.
Muszę, kurwa, muszę.
What? Mute yourself, Rafał.
Co to był za gość? What was the guy?
He should mute himself.
So please tell me, It is okay? This kind of bonus is okay for you?
I'm fine with it.
Yes,
Okay.
it's all right.
It's okay.
Yes,
I think,
yes.
I think it
Yeah,
is.
but
Okay.
where this answer is correct, that is kind of crucial.
Okay, so if I will have a little bit more time, I will send you the information that everything is correct or not.
Okay, thank you.
Did you have to send the calculations or just the screenshot or of the simulation and the formula?
Some people send me the simulation also. Yeah. Some people just write me the or make the screenshot of the paper, but it doesn't matter for me at this moment. More important is that they want to make it, and these people are sending me the answers, some answers.
Okay.
I'm sorry. I
Yes.
have got a question. If I send it like 30 minutes after midnight, does it also count or not?
Yes, today, yes?
Yes.
It was you, yes?
Yes.
Who is it?
Julia.
Julia, okay. Yeah, I see the 4 minutes after midnight, that's right?
I'm not sure.
Yeah, I saw it. I saw what you sent. Yeah, of course, I will take it into account. So, in fact, you will
thank you.
get the maximum point for the Laplace
Thank
example.
you very much.
You're welcome.
So again, some of us are not sure. Just to finish, so if it is possible to do the exam even in the session, like if you're able to give us grades even in the session, then you don't have a problem with the time, right?
I have to ask the dean before.
Dean, yeah, exactly. But if that
know.
is the case, you don't have a problem with the time, right?
Yeah, that's right. Yeah.
All right.
If the dean told me, will tell me that we have to finish before the session starting, then we'll have to make some compression of the time, and maybe we will have to make only one test with whole material. Yeah, that's right. But making also some retake term. Yeah. But I will give you the information maybe today, because I will phone today about this case. And also I will send you by Julia the information about it. Yeah. So as you see, first of all, you have to decide it. You wanted to have the 1 or 2 parts of the test, but more important information will be from the dean.
Yeah, but I am sure they will let us, because like the dean, like the rector doesn't say anything.
No, maybe yes, maybe not. We have to check it. Yeah.
Yeah, exactly.
Okay. So as you see, I've got some homework and you've got some homework. You have to choose how many tests you wanted, and I have to check it. I have to check that it is possible to make it or not. Okay.
Yeah.
Okay. So do you have another questions?
Sir, I would like to talk with you after everybody leaves, please.
After this meeting?
No, in this meeting, but after everybody leaves.
Yeah, everybody is leaving it.
That's my question.
You are the Barry? It is you?
Yep. Yes.
Okay. All right. So I think so please Barry stay with me, okay? And if there's no any questions, so thank you again. And maybe if you have some information about from the deans, I will give you it. And also I will send the information about the range of the material which will be in the next week on the test. Okay?
Okay.
Okay, so thank you for your attention, for this meeting, and we'll see in the next week. And the Barry are staying at this moment. And the last people, thank you again and see you.
See you.
Bye.
Wait, I remembered something actually. I was leaving. Now, our teacher from Maths for Electronics told us that they give time to teachers to grade until 30th of June. So you can ask this also to the deans.
It will be great. It will be great. Yeah, but I have to call to the dean and ask him.
Okay. Have a nice day.
Thank you for you too. See you. Bye.
Bye.